All right. Good morning, everyone. We're going to be going over the 2022 exam for OChem 1 or OChem 2 exam 1. So, okay. We'll start off with the nomenclature like usual. Okay. So in this exam, you have two options whenever you see an epoxide. You can choose well, it would depend on the thing, but you can choose to name it by the epoxide parent chain, or you can choose it by the highest priority. So in this case, technically, the OH is higher priority than the epoxide, right? But I'll go over both namings just in case, so that you guys have both. So just to begin. I'll start with the oxygen naming, with the OH group as the parent chain. So the first step that we want to do, we want to get our chain. So whenever we're talking about an alcohol, we're always going to try to start from the alcohol carbon. So I'll put this at 1, 2, 3, and 4. So we have a butane chain. So if we were going to write the parent name, it would be a 1-butanol. So this is indicating that the OH is on the first carbon of the butane chain, right? And then going on, well, let's start naming substituents. So on 2 and 3, we have it bonded to the oxygen. We won't worry about that right now, but on carbon 4, we do have the bromo, right? So whenever we are looking at the epoxide as a substituent, we call it an epoxy group, right? So let me write that down. So it would be 2, 3. This substituent is called epoxy, right? So if we were to number it, so this substituent will be called a 2, 3 dash epoxy, right? So this is just indicating that on carbons 2 and 3, so these carbons right here, there's going to be an epoxide group that is attached to both of them, right? So that's all it is. And then after that, we can go into stereochemistry. One thing about this problem is that you can have both R and S stereochemistry and cis and trans. So in this one, just because we have two hydrogens here, we can do cis and trans. So in this case, it would be considered cis. But I also want to make sure that because you can do more, wow, that's a lot of people. We can have a lot more. We can have a lot more. How do you say? More compounds are going to have R and S stereochemistry than they are going to have cis and trans, right? So it's better to get into the habit of looking at R and S rather than cis and trans. So whenever we're looking at R and S, we want to look at the two different chiral centers of this molecule, right? So we have a chiral center at carbon 2 and a chiral center at carbon 3, right? So if we're going to look at carbon 2, I'll do that in green. So on carbon 2, the chiral centers are going to be telling us we're going to look at the biggest groups attached to each of these carbons, right? So the biggest group is going to be this oxygen, right? So immediately this is going to be 1. And then going on, we have a hydrogen. This is going to be our 4th group, right? And so now it's between this carbon right here and carbon 3, right? So on this first carbon right here, we have it attached to 2 hydrogens and an oxygen, right? So the OH group right there. So we can just say OHH, right? And on carbon 3, we have it attached to an oxygen right here, a hydrogen, and a carbon. So it's OCH, right? And because this is, we look at the first spot of difference, right? So because this one is the one on the left, carbon 1, is attached to OH and H, while the one on the right, carbon 3, is attached to OC and H. OC and H is going to be a bigger group, right? So we're going to label that as number 2, and label our hydroxymethyl as number 3, right? And so whenever we draw this arrow, this is a clockwise arrow, and there's no reason to flip it at all because the wedge has a big group and the dash has the smallest group. So we can keep this as R, right? So we have 2R. And now if we were to do 3, I guess this is getting a lot to look at. I'll redraw the structure to the right here. All right. So if we're going to look at, this time I'll do it in orange, I guess. If we're going to look at this carbon, the first thing we're going to do, we're going to look at the biggest group. Remember, again, this is going to be our oxygen right up there. And now we have a choice between this carbon, which is attached to a bromine and 2 hydrogens, and this carbon, which is attached to an oxygen, a carbon, and a hydroxy, right? So in this case, this oxygen is going to be a higher priority. So this is going to be, on the left, is going to be a bigger group. So we'll put 2 right here, 3 right here, and 4 right here. And so this way, now we have a counterclockwise rotation, and this is going to be S, so 3S. So stereo is going to be 2R3S or cis, right? You can put cis. Cis is fine in both scenarios. Just in some cases, cis will be incorrect, right? So it's better to get into the practice of doing RNS, right? And to finish off this first naming, so we're going to do 2 namings, one with this pair, one with the alcohol parent chain, and one with the oxygen parent chain. Well, kind of spoiled it. My bad. So, answer for this one, we can. I'll put cis like this, and then 2R, 3S. So both of these are acceptable, and we'll put it in alphabetical order first. So we have 4 bromo and then 2, 3 epoxy, right? So dash 4 dash bromo dash 2, 3 dash epoxy, and then 1 butanol. It can also be 2, 3 dash epoxy butan dash 1 dash OL, butan 1ol. And lastly, we'll do the other naming. So I'll redraw it again. Damn, running out of space. Okay. Okay. So whenever we're naming from the epoxide parent chain, I said it twice now, but the parent chain is going to be called an oxirane, right? And so what an oxirane is telling us is that our oxygen is on position 1 already, right? And so if we're going to look at an oxirane, we're always going to have like between 2 and 4 substituents. Well, not always, but we're going to have between 1 and 4 substituents, right? So on one hand, we have this substituent and like this numbering between 2 and 3, this black numbering. I'll change color for the other numbering. And then this blue numbering, which is 2 and 3 this way, right? So let's see each of these substituents. So I'm just going to write the substituents out without numbering them between 2 or 3, right? So this substituent to the right with the bromine is called a bromomethyl, right? So 1 dash bromomethyl. And then the OH is called a 1 dash hydroxymethyl, right? So, in this, whenever we're naming from the oxirane, whenever we're looking at substituents, we're not going to go by the importance, right? There's a different word, I'm forgetting it, but by priority, right? So in this case, the OH group would have a higher priority than the BR group in terms of the parent chain. But in this case, for oxirane, we're only going to be looking at alphabetical order, right? We're going to skip over that part because we are looking at substituents, right? So in this case, we have a B versus an H, right? So because B comes first, this is going to get the lower number. So this is going to be a 2,1-bromomethyl, and this is going to be a 3,1-hydroxymethyl, right? And so now that we have that, we've already done the stereochemistry, so I'll write it above. We'll start with our 2,1-bromomethyl. So cis-2-1-bromo methyl. And remember to put this in parentheses because I forgot. Dash 3-1-hydroxymethyl. I do believe it's okay to not put 1-hydroxymethyl. I think you can just put hydroxymethyl. I'm just putting it just in case because I'm not sure. And lastly, we'll put our parent chain, oxirane. Right. Any questions on that first one? No one? Okay, perfect. Next one. So in this one, we have an ether. So whenever we're naming an ether is in a similar, I'm forgetting that word again, priority to a halide, right? So the ether doesn't have very high priority. So in this case, we're going to be looking at the priority for the parent chain is going to be with the alkene, right? So remember, whenever we want an alkene, we don't want the longest chain. We want the longest chain with as many double bonds in there as we can have, right? So if we're going to count, we can get this full chain, right? A huge chain, but it's not going to be as long, or it's not as going to have as much priority as a chain that connects these two alkenes with, right? So that's going to be how we're going to start numbering. We'll start numbering from the top. 1, 2, 3, 4, 5, 6, 7, and then make sure we always number backwards. 1, 2, 3, 4, 5, 6, and 7, right? So according to the black numbering, we have double bonds on carbons 1 and carbon 6, and according to the blue numbering, we have double bonds on carbon 1 and carbon 6. Okay, so now if we're going to look at the blue numberings substituents, it would have substituents on carbon 3 and carbon 4, whereas the black numbering would have substituents on carbon 4 and carbon 5, right? So we look at the first spot of difference. 3 and 4 is going to be less than 4 and 5. So we're going to disregard the black numbering, and we're going to use the blue numbering to name our parent chain, right? Okay, so starting off, our parent chain is going to be we already found where which chain where the double bonds were. So it's a 1,6 dash, and so whenever we have 7 carbons, we have a heptane, right? But this becomes heptene, right? And since we have 2 double bonds, that becomes a diene, right? So I'll just try to write that out. Heptane to heptene to heptadiene, right? Because we have 2 enes. We have 2 of them. That's why you add the di in between. And so this is going to be our parent, right? And so now as we keep going, we can start naming our substituents. So subs, right? I'll come back to this sub. First, on carbon 4, we have a 1, 2, 3, 4 carbon substituent. This is a butyl group, so 4-butyl. And on carbon 3, we have the ether group. So whenever we're naming an ether group, we're gonna start with this chain that's hanging off of it, right? So this chain that we have, a 2-carbon chain, is called an it's ethane, right? But as a substituent, we call it ethyl, right? Whenever we have an ether group, that ill gets dropped. So we drop the ill, ethyl, and then we drop the ill, and it becomes oxy, right? So put it together, we have ethoxy, right? So our substituent on carbon 3 is an ethoxy group. And that's all we have for substituents. And now for stereochemistry. Okay, so whenever we have terminal alkenes, we're not going to have any cis or trans, so we won't worry about cis or trans in this one. But we do have a chiral carbon, right? This carbon 3 is our chiral carbon. So whenever we do this, we have to look at everything that this carbon is connected to. So it's connected to the oxygen, the carbon, this carbon 2 and 4. So this oxygen is immediately going to take the lead, and the hydrogen is going to be in the back. And now it's between carbons 2 and 4 to be number 2 and 3, right? So let's look at what carbon 2 is connected to. So carbon 2 is connected to carbon twice, so CC, and then a hydrogen once, right? So it's connected to this hydrogen, so we call that CCH. Carbon 4, same thing. It's connected to 2 carbons, to carbon 5, and then the substituent carbon 1, so C, comma C, and it has an H hanging off, so CCH, right? So whenever we have a tie, we go to the next one. So we would go to this one, and then we can go to either carbon. I think it would be better if we went to the carbon 5 on the parent chain. So whenever we look at that, then we have a C, comma 8. Well, this carbon is a double bond carbon, but it's connected to 2 hydrogens, right? So HH, and then I'll just put C because it is a double bond. And then this top one, we have number 5. This is connected to 1 carbon and 2 hydrogens again, right? But we have more to go on from carbon 5 than we have from carbon 1, right? If we went on from carbon 1, there's no other carbons. But on carbon 5, we can go to carbon 6 and then on to carbon 7 as well, right? So that means that our left one towards carbon 4 is going to be a bigger group, and the right one is going to be a smaller one. So whenever we draw the arrow 1 to 2 to 3, we get something that goes counterclockwise, right? No, it's clockwise. So this is clockwise. So clockwise, this tells us that it is R, right? But because our smallest group is on a wedge, we're going to flip that R into an S. So we have our S stereochemistry. And now if we put it all together, we have our S dash. Remember, we're going to start with the butyl because it comes before the E. So the B comes before the E. So 4 dash butyl dash 3 dash ethoxy. And then 1,6 heptadiene. So dash 1,6 dash heptadiene. And you can also write that ethoxy hepta dash 1,6 dash diene. All right. Any questions on that? Yeah. One more time? Don't we have to mention that it's one, sec or tert? Well, okay. So whenever we did sec and tert butyls, those were going to be in like mostly exam 1s. You're not really going to see those, especially in later exams. And if you do, you can just call it a complex substituent, right? We don't have to one of those like pretend or something. Yeah, like this one would just be a butyl group. This one would be any special butyl group. Yeah.
When you were comparing the priority between carbon 1 and 5, wouldn't carbon 1 has the priority since it has a double bond, so it would be CCH?
Well, right, but carbon 5 also has, it didn't have CCH because we only look at carbons going forward, right? We don't look at carbons going back, right? Just because it has a double bond, I put the C there for clarification, but in that case, we wouldn't count it twice.
And I have a quick question over the steel chemistry of question 1.
Yeah.
So when you on the right,
Yeah.
wouldn't bromine has priority over oxygen? Is the atomic number?
So bromine is bigger, but in this case, because oxygen is also, that carbon is also bonded to like the entire big group rather than just like bromine itself, right? So on the right side, it's connected to just the bromine, right, and 2 hydrogens. If we went on this one, it would be connected to the oxygen, 2 hydrogens, but also like it's connected to this oxygen and this carbon as well. So the one on the left side is actually like a bigger group. Is that, I don't know how to really explain it. It's just kind of intuitive, I guess. Yeah, cis and trans is honestly easier in this case, for sure. Any other questions? Yeah. Mm-hmm. It would be what? Like for the stereo, why is it not S to R? S to R? Yeah. Because it's a clockwise rotation. And so whenever it's clockwise, it would be R. And because we have to flip it, because the hydrogen is on a wedge and the oxygen is on a dash. So because of that, we have to flip them. Because the smallest group is on a wedge. So that would make it go from R to S. Does that make sense? Yeah. Any other questions? No? Okay. No other questions? Okay. Going on. So our final problem, we have ether. So in this one, whenever we start numbering, especially in an ether, we want to make sure that we have the longest parent chain, right? So in this, we don't have any alkenes, alkynes, or anything. We just have the ether. And so we'll start with the longest parent chain, and then we'll look at substituents, right? So if in this case, we have 1, 2, 3, 4, 5 on the right side of the carbon, or on the right side of the oxygen. And then on the left side, we have 1, 2, 3, and 4. So even though the left side technically has more substituents, it would have 3 substituents versus the right side's 2 substituents, right? The right side has this methyl substituent and then the methoxy substituent, and then the left side has the 2 chlorines and the methoxy. So even though the left side has more substituents, because the right side has a longer chain, we're going to be using the right side as our parent chain, right? So our parent chain in this case is going to be a 5-carbon chain, which makes it a pentane, right? So whenever we're looking at the ethers, we're not going to be looking at them as a parent, rather it's going to be a substituent, right? So this pentane is all we're going to write for the parent chain. And then looking up substituents now, we have a 3-methyl, right? And then on the other one is going to be a complex substituent with the ether, right? So this substituent is going to be called, remember, start with the naming of the chain. So this is a butane. It becomes a butyl because it's a substituent. So butyl, and then after that, we drop the YL and add oxy. So we have a butoxy, right? But we have 2 chlorines on it, so we'll call it a 3,3 dichloro. I should have written that first, I'm not going to lie. 3,3 dichloro butoxy. and this is all going to go in parentheses. And because it's on carbon 2 of the parent chain, we'll call it a 2-33 dichlorobutoxy. And whenever we're going to be looking at these, at the naming of this, we don't have any stereochemistry, so stereo, none. So this is going to be our name, right? And so whenever we're looking at this, remember that we're looking at the M in methyl and not the D in dichloro, but the C, right? So we're going to look at that C rather than the one that tells us how, like, what the number is. We're going to be looking at the actual substituent, right? So that means we're going to put the 2,3,3 dichlorobutoxy first, and then the 3-methyl, and then the pentane. So you can just go ahead and do that. Methyl, 3-methyl. Any questions on that? If there are no questions, we're going to go on to the facts section. Yeah. One more time?
If you, would it also be correct to have it as like 3,3-dichlobutyl, that like 1,2-dimethyl-butyl ether? Like, would that work?
So the thing of using 1,2-dimethyl-butyl, so you can, I think you can do that, but that's going to be later on in the exam. I don't think you guys have learned how to name ethers yet, right? So whenever you would do that, you would have a space in between. Or no, I think that's esters. I don't do you,
But also you still have the
yeah, yeah, the parent chain is actually 5 carbons, so it'd just be a 1-methyl, right? Like a 3-methyl, sorry, not a 1-methyl. Any other questions? Okay, going on. So onto the facts section. So in the facts section, we do have a Diels-Alder question, so I'll omit that until the very end. You guys don't need to know this for the actual exam, but I'll still go over it just so that you guys can understand how to work it out whenever you guys do learn it, which should be soon, I think next class. So the first facts questions, rank the following carbocations in order of increasing stability, right? So whenever we're looking at stability for carbocations, so carbocation stability goes from tertiary is the most stable to secondary to primary, right? So let's look at it from that perspective, right? So this carbocation that we have on the left, this is a primary carbocation, which is going to be our lowest stability. So we don't like that. The second one is a tertiary carbocation, and the right one is also a tertiary carbocation. So the one on the left immediately is going to be our least stable, right? And now we have the choice between the middle and the right one of being our most stable one. Notice on the middle one, we have this oxygen that's capable of giving its lone pairs to this to create a double bond, and that gives it resonance, right? So this might be a tertiary carbocation with resonance, right? Versus this one, which this oxygen is not able to give its electrons all the way over there. So because it can't do that, it is a tertiary without resonance. And so whenever we just look at it like that, between with resonance and without resonance, the one with resonance is going to be the one with resonance is going to have a lot more stability than the one without resonance. So our number is going to be 1, 3, and then 2. Any questions on that one? No? All right. So next one, place the following halides in order of increasing reactivity in sodium iodide and acetone. So whenever you have a bunch of these like big words right at the end, one thing that helps is just writing it out, right? So we know sodium is Na, and then iodide NaI / acetone. So whenever we look at this, this should bring you back to OChem 1 exam 2. This would be our SN2 reaction because this is an aprotic solvent. So it's asking us which one of these would be the best in an aprotic solvent in an SN2 reaction. So whichever one is going to be best in an SN2 reaction is going to be number 3 and so on and so forth, right? So immediately on the first one, we see a vinyl halide, right? You know, vinyl halides are not reactive, so we're immediately going to put that at number 1. So as our least reactive. Remember, 1 is least reactive. And now we have the choice between a secondary halide and another secondary halide, right? So the way SN2 reactivity works is that our primary is going to be going to have a higher reactivity than our secondary, and we shouldn't have any reactivity on tertiaries, right? So there should be like no tertiary reactions, right? So because both of these are secondary, we kind of have a little bit of a conundrum, right? So one thing to notice again is that if we were to have anything, this double bond can resonate and can resonate for this bromine, right? But this double bond is unable to, right? And because of that, because this is also considered an allylic bromine, so this is allylic. So when bromine, when a halide is in an allylic position, it becomes a lot more reactive, right? So this bromine, because it's allylic, this is going to be our most reactive. And this bromine that has no resonance with it, no double bonds near it, it's going to be our number 2. Any questions on that? No questions? Okay. On to the next one. So I think this is a new concept that we've learned about Grignard. I don't know if you guys learned this in OChem 1 or just now. So whenever we have Grignard reagent, so Grignard is a very basic reagent, right? So it's basic. So I think you guys have learned this in this exam. Basic attacks the least sub side, right? Least sub. So it attacks the least sub, and acidic attacks the most sub side, right? So because Grignard is going to be in a basic thing, it's going to want to attack the least sub side. So we'll keep that in mind as we go through this problem, right? So the first one, we have an epoxide with 2 methyl groups on either end. The second one, we have the ether with 2 methyl groups on one of the ends. So we know that in Grignards don't react with ethers, right? So immediately we can just put this at number 1 as our least reactive. And now we have the choice between 2 epoxides. One epoxide has 2 groups which are identical on either end, and one epoxide has 1 group which is less substituted, right? So if you were a Grignard reagent, you'd want to attack the one right here, right? Versus on this one, you wouldn't have a preference. So in this case, because this one is going to be more, because Grignard is a basic molecule and it wants to attack something that is less substituted, it's not going to attack the one on the left as readily, right? It's not going to attack the one on the left. Rather attack the one on the right. So the one on the left we'll put at 2, and the one on the right, number 3. Any questions on that? How we got that answer? Yeah. Oh. One more time? Yeah, Grignard does not attack ethers. And then you had a question? Okay. Any other questions? Yeah. So Grignards won't attack ethers? Is that Was that it or? Okay.
That's why it's number one.
Yeah, so that's why that one's number one, and because it wants to attack epoxide, one of the epoxides is less substituted, right? So it's gonna want to attack that one rather than the one that's both has a lot of substituents, right? Any other questions? Okay. On to the next. Place the following resonance contributors in order of increasing stability, 1 being the least and 3 being the most. And then our second part, what is the hybridization of the carbon atom indicated with the arrow? Okay, so whenever we're looking at increasing stability for resonance structures, the first thing we should look at is the octet rule, right? So this first one, whenever we look at the octets, let's just focus on the one with the minus charge on it, right? So this oxygen, if it had a minus charge, it would have 3 lone pairs, right? And that would complete its octet. So we're not worried about that, right? Because if we count the electrons, we have 6 plus 1, 2, right? So we have 8 electrons. The same thing happens with the nitrogen. We have 2 lone pairs on it, and then it has 2 bonds, right? So if we look at that, 1, 2, 3, 4 from the lone pairs, and then 1, 2, and then 1, 2. So that becomes 8 electrons on the nitrogen. So that also completes the octet rule. But this carbon, it only has the 1 lone pair, right? And so because it has the 1, 2, 1, 2, this only has 6 electrons. So it does not complete our octet rule, right? So from that, what we can say is that because this doesn't complete our octet rule, it's immediately going to be our least stable resonance contributor, right? And so now it's between the oxygen and the nitrogen, right? Across both of them, both are, I guess, relatively electronegative atoms, right? The nitrogen comes and then oxygen comes, so it's carbon, nitrogen, oxygen in the periodic table. But electronegativity goes towards the right and then goes towards the up as a periodic trend, right? So between nitrogen and oxygen is going to be a more electronegative atom, right? And because of that, it's more comfortable carrying the negative charge than the nitrogen is, right? So we want this negative charge to be on the oxygen, which makes the oxygen one be the most stable resonance contributor, and the nitrogen the second most, right? So that's going to be our numbering for the resonance contributors, and then the hybridization of the carbon atom. So if we look at this one point, we have an sp. Technically, this has a hydrogen, I guess. sp with the lone pair. So spp, right? So this is an sp3 carbon right now, right? And then the one on the left, if we remember, if we just put sp3 in here, this would be incorrect because we have to look at all of the resonance contributors for the actual hybridization, because the lowest hybridization is always going to be the actual hybridization, right? So on this left one, in this middle one, we have this as an sp with 1 hydrogen attached to it, sp2. So this carbon is sp2 versus this carbon's sp3, right? And then the same thing happens here. This is an sp2 carbon. So because of that, because we have 2 sp2s, 1 sp3, even if we had 1 sp2, it would always be sp2 in that box, never sp3. So sp2 is going to be our answer here. And are there any questions on that? Any questions at all? No? Okay. So this is a Diels-Alder question. I'll come back to that at the very end of the very end. So don't worry about it. So next one. So answer the following questions for the molecule below and place the answers in the appropriate boxes, right? So how many signals would be observed in the H NMR? Okay, so we'll start with the first one. How many signals would be observed, right? So whenever it's asking this question, we're gonna look at every single unique hydrogen, right? Unique hydrogen. So if we look at this, Let's start from the left side. We have this CH3. We can call this hydrogen 1, right? But we have another CH3 attached to the same carbon, right? So if we were to put it like this, even if we just put it like that instead of having it off to the side, if we were to flip this molecule over, both of those CH3s would be the same thing, right? So this CH3 is also going to be 1. So I'll draw that onto the left side. So we have two identical hydrogens. So those are both going to be labeled number 1. Then the hydrogen attached to the A, number 2, going on 3, 4, right? Because these are in two separate, this CH2 and this CH2 are in separate environments. This CH2 is attached to a CH, while this CH2 is attached to the O and the CH2, right? So that's 4. And then after the oxygen, we have our 5th, so this HB. And whenever we have double bonds, so one thing that we can't take the liberty of doing with double bonds is just rotating them at will, right? So double bonds are kind of stuck in their positions. So because of that, all of these hydrogens are actually in different environments. So this hydrogen, this first CH, is going to be number 6, and then the CH on the bottom is going to be our number 7, and then on top is going to be number 8. And that is because they can't move across and like rotate. This hydrogen is always going to be across from that big group, and this hydrogen is always going to be across from this one hydrogen, right? And because they can't switch positions, that's going to be how it's going to be the entire time, which means they're always going to be in different environments, right? So that's why we have 8 different signals. Now, on to the multiplicity. So whenever we have a multiplicity of carbons, we're going to look at the carbon that the hydrogen is attached to, right? So multiplicity of HA. So we're going to look at this carbon, right? So this carbon is attached to this carbon, and this carbon, and this carbon, right? It's attached to 3 carbons. So for every carbon that we have to have a it's going to be multiplicative between them, right? So in this case, because we have 2 identical carbons, it's going to be a slightly different rule. So normally we would do 3 plus 1 times 3 plus 1, right? If there were 2 non-identical carbons. But because they're identical, instead of having 3 plus 1 times 3 plus 1, which would give us 16, we have 3 plus 3 plus 1, right? So we have 6 hydrogens. It's essentially saying we have 6 hydrogens, and then we add 1. And then that's going to be multiplied by the one on the right, which has 2 hydrogens plus 1, right? So this carbon is only connected to 2 different unique carbons. 2 different unique carbons. So this is one unique carbon, and this is another unique carbon. And this first unique carbon is connected to, it has 2 things which are identical, which is why we put them as this 3 plus 3, right? So if we were to multiply this all together, this would be 7 times 3, and that gives us 21 as a multiplicity, right? Multiplicity of HB. So whenever we're looking at multiplicity of something that's connected to an oxygen, we're not going to go back, right? So even if the oxygen was attached to attached to a hydrogen, the signal would only be observed whenever it's in ultra pure conditions, right? So, or theoretically predicted, right? So if it says theoretically predicted, or if it says in ultra pure conditions, that's when you would take an OH into account. In this case, even though it says theoretically predicted, this oxygen does not have a hydrogen attached to it, right? So we're not going to worry about it. Now we look to the right, and this carbon is only attached to one other carbon, right? So this carbon is just going to be a 1 plus 1. And so it'd be a doublet, so 2. You can also write D for doublet if you wanted to. I think it's just better if you guys just, put that number. I think it's easier for everyone. And so now, finally, what is the multiplicity of the signal for carbon C in the proton couple C13 NMR, right? So whenever we're looking at multiplicity of carbon C, we're looking at the multiplicity of the carbon, right? So whenever we're looking at that, we're only going to look at the hydrogens that are attached to that carbon, right? So that's going to be 3 hydrogens. And we're going to do the same thing, 3 plus 1, and that's just going to be our number 4. So the final multiplicity of CC is 4. Any questions on how I got any of that? Anything you guys are confused about? Yes. So whenever it says theoretically predicted, or if it says ultra pure conditions, that's the only time you'll see any proton NMR with electronegative atom, right? So in this case, oxygen, right? That's when, if you had an OH, you would see a 1H, right? But whenever it's not in theoretically predicted, or if it's not ultra pure, then you can just disregard that. That OH doesn't mean anything, like in terms of the proton NMR. Yeah.
How do we calculate the multiplicity of one of the equations on the double bond?
Oh, okay, that's a good question. Okay, so he asked, how do I calculate the multiplicity of a hydrogen on a double bond? Okay, perfect. So let's say I'm gonna look at this 6th one, right? So this one right here. So I'll do this in a different color. So let's say it said like HD, right? So we have HD, and it's we want to know the multiplicity of HD. So I'll put V HD. Okay. So whenever we're looking at that, we're gonna look at every single like opposite that it's attached to, right? So this is connected to this. This HD is connected to this carbon as well. Is connected to this carbon. Sorry. And so whenever we're seeing this blue circle carbon, we're gonna go to each of the carbons adjacent to it, right? So let's go to the left first. So the first part of our equation, we'll just put the 2 plus 1, right? Because that's connected to the CH2, which is also the unique, right? And then on the right side, we have another CH2, but this one has hydrogens in 2 different planes, right? So whenever we would do that, we wouldn't just do another 2 plus 1, right? Because that would be putting them in the same plane. We don't want to do that. So what we're going to have is actually 2 1 plus 1s. So we're going to have multiply 1 plus 1 and then 1 plus 1 again, right? And so if we get all that out, 3 times 2 times 2, that gives us 6, 12. So our multiplicity for that would be 12. That makes sense? Right. Any other questions? Oh, sorry.
So they were asking to do like counting the oxygen, how would that be?
So it would just be the 1 plus 1.
Count the oxygen.
Yeah, because you're just attaching, counting the hydrogen attached to the oxygen.
In that case, it wouldn't say theoretically predicted or not predicted.
Yeah.
Right?
If it said theoretically predicted and ultra pure, then you would count it. Otherwise, you wouldn't count it. Does that make sense? We didn't count it there because this time it didn't have a hydrogen attached to it. So even though it was theoretically predicted, the oxygen didn't have anything attached to it. So even if we did like theoretically predicted this HB, right, HB, so we would have 1 plus 1 times 0 plus 1, right? Because this oxygen isn't attached to anything. So we would still have 2, right? But if this OH if it was like an OH right here, right? Say we had OH, it would become 1 plus 1 times 1 plus 1 again. And this would be 4, right? Any question? Any other? All right. So onto the reaction section. So this first reaction is going to be an alkane reaction. So we'll start with the first step. Our first step is going to be an addition of a Br and an OH on a mark. So mark addition. And these are also, I think it's an anti-addition as well. Anti-addition of Br plus OH, okay? And so in this case, OH is going to be our bigger group than Br. So whenever we do this, we'll put OH right here and Br like this. So this way we're keeping the anti-conformation. If it wasn't if it was like a syn addition, maybe we would like put the Br like this, but because it's anti, keep one up, one down, right? So that's going to be our first step. Second step, this is intermolecular Williamson. And what this does, whenever you have a 1,2 halide, like the alcohol is one away from the halide. I think it's geminal halide, right? Whenever you have a geminal halide, then it's going to create an epoxide. So we have an epoxide forming between this and that, right? So we'll do that. Epoxide has been formed, right? One more time? Yeah, it formed an epoxide. That's pretty much it. And then third one, HCl ether. So remember, HCl is an acid, right? So we have an epoxide, so we do have to make sure that we look at the acidic conditions. So whenever we have an HCl ether, this is an acidic reaction. And what that's going to do is that it's going to attach the Cl onto a more sub side because acidic attacks more sub. Right? And so what that's going to do, that's going to push off, that's going to break this bond with this oxygen. It's going to push it off and it's going to protonate this oxygen with this hydrogen, HCl, right? So that's going to become an OH, and then you're going to have a chlorine right over here. What that's going to look like is like this, OH, and then we'll put our Cl right there. And then lastly, we have PCC. So PCC is a weak oxidizing agent. And whenever a weak oxidizing agent goes onto a primary halide, not primary halide, primary alcohol, we have an aldehyde forming. So lastly, just this double bond O, and that Cl is still there. Any questions on that? So whenever we have a primary alcohol, if it said Jones reagent or like the sodium dichromate reagent, that is going to be a strong oxidizing reaction, right? And so if we have a primary alcohol like this, instead of that, if we had Jones, so let's say alt Jones, this step number 4 would give us a carboxylic acid. So it looked like this, just the OH, right? So because it just says PCC, we're only able to get it from an aldehyde or a ketone, right? And because it's a primary, it's always going to be an aldehyde versus a ketone. Don't have any other carbons. Any questions? No question. All right. Next one. So H3O, 50 degrees Celsius, right? So I think this is a new thing that you guys have learned, right, about the heat. So whenever there's heat, there's going to be whenever there's cool, so 0 degrees Celsius, we're going to have a less subbed alkene. But whenever we have 50 degrees Celsius, we want the more subbed alkene. Okay, and so putting it into practice here. So this H3O, what it's going to do, it's going to protonate one of these double bonds, right? And we have to figure out which one is going to protonate. So that's our first step between major, and then we have to figure out the major and minor contributors, right? So our first step is to decide which one it protonates. So we have 4 spots that it can protonate at, right? If it was to protonate at, let's call each of these spots a different name. So I'll say 1, 2, 3, 4. If it protonated at 1, right, then it would have a positive charge on number 2, right? And this becomes a secondary secondary carbocation with resonance, right? And I'll do that for number 1. For number 2, for the second position, we would have a plus charge over here, right? And then this one would have just number 2 on it, so we wouldn't worry about that. This one would just be a secondary carbocation. Our third one, if we protonated that, we would have a plus charge right over here. If we protonated this with the hydrogen, right? This would give us a secondary carbocation again. And then the fourth one, if we protonated this fourth one, this third would have a plus charge on it, right? And that would mean that that's a tertiary carbocation with resonance. So between all of these, that means that the one that's the most stable is going to be the one that's protonated. So this tertiary carbocation with resonance is going to take it, right? So that means this oxygen or this carbon gets the hydrogen, this bond breaks, and this carbon gains a plus charge. So what we're going to do is we're going to go ahead and redraw that as like that. So we'll do this, double bond onto this like that, and then plus charge right here, right? So that's our first step, right? And now we have to decide between a major and minor contributor. So H3O plus, what it's going to do is going to add an OH, right? But because we have resonance, we have 2 contributors that we can go to, right? We have that resonance contributor, the one that we just drew. And then if we move this double bond over, we have one that looks like this. 1 second. And then the plus charge would be right over there, right? So to decide between which one is major and minor, we're going to look at this temperature. So this temperature tells us that the more subbed alkene is going to be our major contributor, right? Because it's in 50 degrees Celsius. So let's look at the subs of each of these alkenes. So this first alkene that we drew, this has sub, right? So let's call that sub. And then the one on the right has 1 sub, 2 sub, 3 subs. So it has 3 subs. And because the most subbed alkene is going to be our our major contributor, this is going to mean that we put our OH on this side for the major contributor. So our first major is going to be like this, with the OH sitting right there. And our minor contributor is going to be where this OH is on the tertiary carbocation. Right. So if we just redraw that, and then we put our OH. And these would be our major and minor. If it said 0 degrees Celsius, I'll rewrite that in. So 0 degrees Celsius. This would just make this minor and major, right? Because we want the major to have less subs and the minor to have more subs, right? If it was a 0 degrees Celsius. Any questions on that? How I got to that answer? Yeah. Oh yeah, I missed one. Yeah, sorry about that. Yeah, red is backwards. If it was a 0 degrees Celsius. Right. Any other questions? All right. Next one. So HI excess in heat. So this is kind of like an SN2 reaction, I guess. So what this is gonna do is this is gonna cleave this bond right here, and it's going to cause this hydrogen to attach to this oxygen right here. So this becomes an OH. This iodine, where this would have been a plus charge, this iodine is going to take that place right there. So to put it simply, it just cleaves it and then takes its place. Right. So if we just draw it. This would become OH, right? And now we have a 1, 2, 3, 4 carbon chain. 2, 3, 4. 1, 2, 3, 4. Perfect. And on carbon 3, we have our iodine. So this would be our product for step 1, right? So let's say that. Yeah.
The H be that side of the bond, or like the bond oxygen and
Okay, that's a really good question, actually. So if you were to do it right here, then this would create a a vinyl halide, right? So the iodine would be right on off of that double bond, right? And that's just energetically unfavorable, so it wouldn't do that. That makes sense? Beautiful. Yeah, I should explain that earlier. Sorry about that. So next step, so number 2, CH3OH in heat. So this is going to be our SN1 reaction. So what we remember about SN1 is that it just takes out the halide and it replaces it, right? So we'll draw our benzene ring, OH, and then we have our OCH3, right? This NaOH, again, this is going to be a different kind of NaOH. So where before we had the intermolecular Williamson NaOH, which created the epoxide, this oxygen is not going to be able to do that, right? So in this case, all this NaOH does is that it takes that hydrogen off that oxygen. So it becomes an O minus, right? Which makes it into a good base. So for number 3, we have our O minus Na plus, then our OCH3, and our final step, CH3Br. Just again, this is going to be just an SN2 reaction, because remember, this is a primary halide reacting with a base. So primary halide reacting with that base, that gives us an SN2 reaction. Essentially just puts the CH3 onto that oxygen, creating a diether. So this becomes our OCH3, 1 ether, and then we have our second ether right here, OCH3. Any questions on that? No questions? Yeah, sorry.
First, so NaOH can either form an epoxide or add the Na to the alcohol.
Yeah. So it forms an epoxide whenever it has a geminal halide attached to it, right? Whenever we had that Br there, it wanted to attack, and that's why it created that epoxide. Versus over here, it didn't have any halide to attack this between this second and third step.
So the Na replaces the hydrogen.
Yeah, it just replaced the hydrogen with the minus charge. No worries. Yeah. Yeah, OH would be deprotonated, and then it will also attack it in the same step. So yeah. Yeah, the NaOH deprotonates it and then adds the Na plus. So same way, so this NaOH becomes like an H2O. It takes that hydrogen, becomes an H2O, and the Na gets attached to that oxygen. And so that's why it's that O minus Na plus, right? Any other questions on that? All right. So fourth question, NaNH2 150 and then H plus. Okay. So in this, we have a terminal alkyne producer. So this creates terminal alkynes, right? So this is important. This then H plus, right? Because one thing to note, this NaNH2 150 degrees Celsius is going to create acetylide, right? This creates acetylide, right? And that's our triple bond with the minus charge at the one end. This then H plus essentially just protonates it in one step. So it just becomes a triple bond, right? So because of this H plus, we're not going to have a minus charge on that. It's just going to be a regular triple bond. and this is going to be on a terminal carbon. So essentially, these BRs, they're leaving, and then we're going to have a triple bond right there on a 1, 2, 3, 4, 5 carbon chain. So if we did that just like this, 1, 3, 4, 5. So we have a 1, 2, 3, 4, 5 carbon chain, and that's going to be the product of our first step, right? The next step, AgSO4H2SO4H2O. So what you guys have to know about this is that it creates from a alkyne. It's a oxidation reaction that makes an alkyne become a ketone, right? So not aldehyde, just ketone. So what that means is that because we have a terminal alkyne, this can only go to one place, right? If it was going to come here, it would become an aldehyde, and it doesn't create aldehydes, it creates ketones, right? So over here, we would have a double bond O coming off, right? So for the next step, we create a ketone. So we have our double bond O, 1, 2, 3, 4, 5. So our 5 carbon chain is a double bond O. And even if you didn't know what we had, if you look at this, you can kind of, I think it looks very similar to a Grignard reagent, right? And Grignard reagents love attacking these partially positive carbons. And this double bond O, this ketone, creates that perfect environment for like a Grignard reagent to attack, right? So this is kind of just the same thing as the Grignard reagent. I forgot what it's called. It's not. I know it's acetylide, but I don't know what kind of reaction it's called. Not Grignard reaction. But step 3, it just attacks right here. This gets the double bond gets over here in the minus charge, and then H3O plus, this comes and protonates it. Right. Well, I guess I should have drawn that better. So like that, it protonates it. Right. And so what we have is an alcohol. So we have our secondary alcohol attached to a carbon, the triple bond to another carbon with ACH3. That makes sense to everybody? Any questions? Yeah. One more time. The double bond on 4 and 5. Yeah, you can put it on 4 and 5. That's fine. They're both the same thing. Any other questions? The only way you wouldn't be able to is if it had like a methyl group like right here, right? Because then you wouldn't be able to have 5 bonds on one carbon, right? So only in that case, then you would have to go between 1 and 2. But because this one doesn't have any substituents on those carbons, it would be able to go either way. Any questions? Any other questions? All right. So next one. LiAlH4 and H3O plus. So this is a it's a reduction reaction. So it's a strong reduction reaction. And so whenever this is done with an ester, it actually causes it to cleave, right? So we have an ester here, and so this double bond oxygen and this oxygen, they cleave and they become 2 separate entities, right? In this case, we have a 1, 2, 3 carbon chain and a 1, 2, 3 carbon chain, all bonded to an oxygen, right? So in this case, we would have 2 of the same thing, right? Whenever it cleaves. Whenever we do that, we can just have this OH, right? Because whenever it cleaves, it also protonates this oxygen. So it becomes an alcohol, right? So our first step is that you don't have to put that it creates 2 of them at all, especially if they're identical. I'm just putting it for simplicity's sake, or not simplicity's sake, just so that you guys know that it would create 2 of them, right? Not just 1. It would create 2, but I mean, they're the same thing. So you only have to draw 1 on the actual exam, and you don't even have to say that it did 2. Whatever, I'm going on. Anyway, second step, sodium dichromate. So this is going to be our the strong oxidizing, right? And in this case, remember we have a primary alcohol, and whenever we have a strong oxidizing reagent such as Jones or sodium dichromate, so Jones would also apply here, we get that primary alcohol and it becomes a carboxylic acid, right? Double bond O, OH. So now that the OH becomes and it suddenly gained the carbon as well. My bad. So so it should have 3 carbons. Double bond O, OH. Okay. So that is our carboxylic acid that we have. Our third step. This is Fischer esterification. And it's in the name, esterification. We want this carboxylic acid to become an ester, right? So whatever we do, it's always just going to be adding this OCH3 group, right? Or OCH2, CH3, whatever it may be. It would add that group on to this carboxylic acid and make it an ester. So our step 3 is going to be double bond O with our OCH3, okay? And lastly, we have our Grignard reagent, right? It doesn't say excess here, but in this case, we actually do this 2 times because this is an ester, and technically that OCH3 is considered a good leaving group, right? So because of that, this MGBR, whenever it attacks the first time, so let's say it attacks, this oxygen gets its minus charge, right? But then that minus charge wants to balance itself. It creates that double bond one more time. And whenever it creates that double bond, we actually have 5 bonds on that carbon. So that's going to kick this OCH3 off, right? And then that'll cause the MGBR to attack one more time. And then the same thing happens, except this time the minus charge isn't able to create that double bond again. And it gets protonated by that H3O+, which creates that alcohol. And it kicks off this OCH3. So the end product of that will be our OH. Wait, too many carbons. So OH, and then we have 2 groups coming off with the benzene rings. Any questions on that? I already got that answer. No questions? All right. This is a Diels-Alder question, so I'll come back to it at the end. We're almost there. All right, mechanism. So first step for mechanism. This is an H3O thing. Kind of looks annoying, just because of this entire thing, right? But what we do know from this, we have at least 2 ring closing, right? So we have 1 ring closing that would create this right here, and we have another ring closing that would create that ether. So to do that, first step we would need to do is notice that this oxygen has 2 lone pairs, and those lone pairs love to attack hydrogens. So because we have an acidic solution, H-OH2 at the plus charge, we want to draw that arrow attacking that hydrogen, and then that hydrogen cleaving its bond with that OH2, right? And so the first step that we're going to have is our this, and then this O touch the H with our plus charge, okay? So next step. So next step that we can do here is we can remember that this double bond is actually electronegative. And so what that means is that it wants to attack anything that is partially positive, right? So because it's partially negative, even though this oxygen is technically positive, this double bond would rather attack this partially positive carbocation, or not partially positive carbon, right? Because on an epoxide, this is going to be in acidic conditions as well. H3O is acidic. So whenever it attacks this, it would create this ring closing bond, which would create our 6-carbon ring. And it would break this off, which it wants to do, right? Like this bond wants to break so that this oxygen can have a neutral charge on it, right? So it would attack this partially positive carbon. So whenever we look at that, we can start counting since we're doing a ring closing. So 1, 2, 3, 4, 5, and 6. So whenever we draw our next arrow, we can draw our cyclo, right? And then let's number it 1, 2, 3, 4, 5, 6. So on carbon 1, we have nothing attached. On carbon 2, we have a methyl, so we'll add that. On carbon 3, nothing. 4, nothing. 5, nothing. On 6, we have our methyl group. So 6, we have our methyl group. And then we have our carbon and OH. So CH2OH. Right? So this is what we have now. Right? And now, finally, let's put the charge where it needs to be. So whenever we created this bond was broken, right? So carbon 1 got its bond back, right? It broke a bond, but it also gained a bond. But carbon 2, it just broke a bond. So that means carbon 2 is going to have a positive charge on it, right? And so now we have the steps to get our second ring closing back, right? So we have this oxygen with lone pairs that loves to attack positive charges. So let's let it. It's going to go and attack that positive charge, right? And so whenever we do that, we create a ring as well. So if we were to count oxygen as the first, it would be, well, not the oxygen, but this carbon first, 1, 2, and then this third piece, right? So whenever we have that, we would draw our cyclo like this and this, right? Then this would be our first carbon. This would be connected to oxygen, which is number 2, and then that is connected to this, right? So it's kind of coming together, right? But this oxygen has a hydrogen attached to it. So our final step, we're going to deprotonate the oxygen. And what we can do that with, we've created this H2O, right? So this H2O has lone pairs that likes attacking and taking hydrogens, right? So it takes this hydrogen, that bond breaks, and we have our final product, right? So it was a short mechanism, a little bit tricky, but we got there in the end. Any questions on that?
Draw the arrow going back, right?
Yeah. Yeah, you do. So I mean, you don't have to draw this arrow that I drew here. Another thing you can do is just like draw this structure again instead, and then just like box it in. However, I just like to draw the arrow back to the original structure to show that the structure is complete. Right. Any other questions? All right. So next we are doing synthesis. All right. So for synthesis, the first thing that we see is that we have an OH group, and we have it on a place that we can actually do Grignard, right? But if we were to do Grignard here, we'd have an MgBr on a vinyl position, right? Thank you so much. It's on a vinyl position. So because of that, we actually do not want to start with that, right? So our first step is not actually going to be then H3O plus, right? Our first step, we're going to want to create this double bond, right? Because if we can get rid of that double bond, then maybe we can put something there instead, right? So the first thing we can do is H2 and Lindlar's catalyst. So what H2 and Lindlar's catalyst does, it's a reducing agent, right? But whenever it comes into contact, what H2 and like palladium, right, or platinum, those heavy metals, whenever it comes into contact with an alkyne, it reduces it all the way to an alcohol or alkane, right? But whenever we add Lindlar's catalyst, it stops at just the alkene, right? So what we can do here is instead of just taking away the double bond, we make it into a triple bond, right? So OH, that, and then triple bond bonded to one chicken leg. Oh, and sorry, we should have noticed alcohols, alkenes, alkynes of 3 carbons or less, okay? So always make sure to look at that. I forgot to, that's my bad. So to keep going, what we can do now is we have an alcohol, but we also have a triple bond, right? And we know that triple bonds love attacking and creating bonds. So what we can do here is do that same Grignard thing. It's not called Grignard, but it's the acetylide attacking the ketone, right? And so what that'll do is that'll create that that'll create a ketone, and that'll be attacked with. Make sure to put then H3O plus. So, and that'll be attacked with an acetylide anion, right? So this minus charge gives it that that oomph to start attacking, right? So I'll start with the left side just because we just have to do one step. So if we do PCC or Jones or sodium dichromate 207, if we use any of these, all of these would create our secondary alcohol, right? Because it's secondary, and we can just circle that. That's fine. So that's our starting material on that side, right? But now we have to create acetylide, right? So whenever we're creating acetylide, what we can do instead is that we can just do that NaNH2 150 degrees, right? 150 degrees without the H3O plus. So if we added, or H plus, right? If we added H plus, it would become just a regular terminal alkyne, right? But because we just added the 150, it creates a terminal it deprotonates the terminal alkyne, creating acetylide, right? So we have our terminal alkyne right here, right? And the next step that we can do is just get rid of the terminal alkyne, right? So this terminal alkyne, what we can do with it is that we can make it into a SN2 reaction, right? So this is technically, if we were to do something like this, this minus charge, or actually I'll draw it, CHC minus, right? This would definitely attack this carbon, which would have a bromine on it, right? If this had a bromine, then they would attack that partially positive carbon. So let's draw that. So if this reaction were to take place, Na plus, this carbon would attack this, and it would have an SN2 reaction, right? Because it's primary halide. So that gets rid of our triple bond, and we can just do the same NaNH2/150, and that will get rid of our minus charge, and we have our triple bond, or with 2 carbons, so alkyne of 3 carbons or less. So this is completely fine, right? And now lastly, we have our Br. There's a lot of ways we can get rid of this Br. One of them is to do HBr ether, or HBr with peroxide, right? We can also do PBr3 and then use Grignard. But there's a lot of ways to get rid of this, right? I'll opt for the easiest way, PBr3. So I'll also show you the other way. So PBr3, and this will allow it to become an OH. And that causes it to have, okay, so this, whenever it becomes an OH, then we can do Grignard onto it, H3O. So whenever we do that, then this becomes an formaldehyde. So it becomes 2 H's on either side of that carbon, right? And then this will also be done with this MgBr. And we have our, if we go to the left side again, sorry, we do PCC, and we create our CH3OH. So that is a primary alcohol, 1 carbon. So it fits the description. We can use Mg/ether, and that'll get rid of that Mg. And so now we have Br coming off of this, and now one more PBr3 will take it completely off and give us that OH. Did I mess something up? I did. Yeah, I put the Br, and then that gives us our 3 carbon alcohol. So if we were to have this, we'd have the OH right here, and that's another 3 carbon alcohol. And I tell you guys that would give you another way as well. So if we were to do HBr / peroxide, so what this does, HBr peroxide, it's an anti-mark addition. Mark addition of H and Br, which means that the Br would go on the less sub side, right? And so what we would have is an alkene now. This is technically a 4 carbon alkene, so we can't use this as a beginning. But what we can do is we can just turn this into an alcohol with the H2SO4 and heat. And that gives us our OH right here. And however we want to do it, we can have multiple chains cut off at the same time. We could have all 3 chains cut off, right? And then, we just have to cut off 1 chain, right? So if we did then H3O plus, we create a ketone. And since we already created a ketone like this, we don't have to draw this again. So this is fine. Plus our CH3 MgBr, right? And so that would be also a valid starting at the MgBr, Mg/ether and CH3-Br, and we can do our PBr3. Or we can even do Br2 and light, however you want to do it, because I think alkanes are allowed. Nope, alkanes are not allowed. We have to do PBr3. That gives us CH3OH, and that's also valid. All right, so there's 2 ways of doing that side, I guess. Any questions on any of that? No? Okay, and last question. We do have spectroscopy. So from now going forward, you're going to continue having spectroscopy problems. There shouldn't be too bad. I feel like they're more of a puzzle than anything else. So I'll try to help you guys understand some of it if you guys don't already. So the first thing you should look at whenever you look at a spectroscopy problem is the top, right? C9H12O2, right? So what this tells you is that, you have 9 carbons, 12 hydrogens, and 2 oxygens. So we're going to figure out places to put them, right? So the first thing I want everyone to know is the unsaturation number. So one important thing about the unsaturation number is that whenever you any number greater than 0 in the unsaturation number means you have a double bond. Okay, so unsaturation number of 1 means you have 1 double bond. Unsaturation number of 2 means you have either 2 double bonds or a triple bond. 3 is either 3 double bonds, a triple bond, and a double bond. I think that's it. And then 4 means you have a benzene. And anything higher than that, you go back to the 1, right? So if you had a 5, then you have an extra double bond on top of that benzene. Okay? So let's look at how to calculate unsaturation numbers, right? So unsaturation number is calculated by 2C plus 2 minus hydrogens plus nitrogens. So we're not going to worry about nitrogen right now. Just know that it will be coming up on your unsaturation number. So if we did all divided by 2, so if we did this, we would have 2 times 9 plus 2 minus 12 all divided by 2. That gives us an unsaturation number of 4, right? So remember, whenever we have 4, it means we have a benzene ring. Okay, so because of that, we use all 4 of our unsaturations. So benzene ring only has 3 double bonds in it, right? But it counts as 4 unsaturations. So because of that, we know we have no double bonds in the rest of the molecule. The rest of it is all going to be single bonds, and all 4 of our double bonds are using that benzene ring, right? So we start off with the knowledge that we have a benzene ring. So first thing I look at, I just look at if there's anything on this spec IR. So I don't normally like to use this, but in this case, we have a very large OH peak, right? So this is our broad OH peak, so let's call this OH, right? Nothing else really stands out to me, so we can maybe use this as like a guide. Mostly, I like to look at this proton NMR, right? So in our proton NMR, we see, I like to go downfield first and then go back to the main field. So the most downfield thing we have is this 4H doublet doublet, right? Whenever we have a benzene and a doublet doublet structure, what it tells us, especially in this 7 to 8 range, which this is very close to be in. So in the 7 to 8 range, 7 to 8 ppm, it tells us that we have that's the benzene range, right? And so what this doublet doublet structure tells us is that it is a para-substituted benzene. So this benzene that we have has 2 substituents on it on opposite ends, okay? And now we'll go back to the start, very start. Okay, so the first thing we have, 3H, so this CH3, let's box that, and that is looking at this is a 3 peak, so this is looking at a CH2, right? Okay, it's fine. It's not that downfield, so maybe, so the CH3 is not attached to anything that is electronegative at all. So this CH2 might be though, because if it was a completely not deshielded, then it would likely be like around like 0.7 or 0.8, right? But because it's slightly down there around 1.4, we'll say it's like slightly deshielded. So right. So now I'll skip this 1H peak because this 1H peak just tells us like something hydrogen is attached to a 0 carbon thing. So if I was just to put C. So then we'll go on. So on the 4 peak, so this is getting really, really far down. It's more very deshielded. So we have a 2H, so CH2 bonded to a 3 carbon thing, CH3. And one thing to notice here is that this CH2 is quite downfield, right? So it's probably connected to an electronegative atom, right? So an oxygen in this case, right? But you also can notice we have a CH2, CH3 that is slightly downfield, that is pretty downfield, not slightly. And we have a CH3, CH2 that is slightly deshielded, right? So what that can mean is that these CH2, CH3 and this CH3, CH2, they're both the same groups. They're just 2 different carbons of the same group, right? So this one, the left one is this CH2 and the right one is that CH3. So we found 2 of our carbons because we found 2 of our carbons already, right? We have 6 carbons in the benzene ring and then we found 2 carbons and we only have 1 left, right? And then this last one, we have this 2H peak, so CH2, looking at no carbons. So looking at C, and it's, if you think about it, this is very downfield, so it has to be connected to an electronegative atom, right? But it's that electronegative atom is not, doesn't have any, what's it? It doesn't have any hydrogens on it either, so no hydrogens. Or actually, it could. I don't know. It doesn't say if it's. Okay, it does not say that it's ultra pure, so we're gonna assume not. So it's connected to an electronegative atom, right? That's CH2. And so totally, what we have is we've found 3 of these 3 carbons, right? So we found this. We found this carbon and this carbon being the same. So these two, we have two of those carbons. And then another group, we have this CH2 bonded to a C, which is bonded to an electronegative group, right? So now that we have all of that, we can start brainstorming as to how it's created, right? So one thing I like to look at as I'm brainstorming is this carbon-13 spectra, right? And so whenever we look at this, we know that we don't have any double bonds aside from this benzene ring, right? So esters, aldehydes, ketones, all out the window, right? So we know no esters, no aldehyde, no ketone. So that means these oxygens must be either ethers or alcohols. Okay, does that make sense? So we have either ethers or alcohols, right? And because we have that OH peak, we can safely say that we have at least one alcohol in there. Okay, so we just have to figure out where it is. So if we were to put all of this together, let's look at this carbon-13 real quick. So if we look at where the alcohols and where are they? Okay, alcohol are either 50 to 90 range, right? So if we look between 50 and 90, we have two, right? We have two things. One is going up. Both of them are going up pretty high. So that means we have two of them alcohols either. So our prediction is correct, right? And let's see if we can find anything else. We have the OH stretching. Let's see if we can find anything for ethers, right? So that's their calls, phenols. Okay, can't really find anything for ethers. It's okay. Okay, now that we've like exhausted all options, we can start creating the molecule, right? So we have our double bond or our benzene ring. It has two substituents. Okay, one of the substituents is a CH2 connected to a carbon, which is connected to an electron withdrawing group, right? An electronegative atom. So this CH2, what we can do is have this CH2 right here, right? And this CH2, if we say it like this, it's connected to this, which is just a carbon, right? So if it's connected to this carbon, we can also say it's attached to an oxygen. And this oxygen would have a hydrogen attached to it. And I'll show you how I got to that conclusion after I draw the next one. So the next one, we have a CH2 bonded to a CH3, right? But then we also have something attached to the CH2, which is electronegative. But that CH2 also is not bonded to a carbon. Why? Because we know that it's bonded to something electronegative. And if it was that carbon, then it wouldn't be that downfield, which means that this CH2 has to be bonded to an oxygen, right? And because we have an ether, this second one is going to be our ether with our CH2, CH3. And now we have gotten all 9 of our carbons. So if we count 1, 2, 3, 4, 5, 6, 7, 8, and 9 carbons, 2 oxygens, and all of our hydrogens should be there. We have 1 hydrogen, 3 hydrogens, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is going to be our final molecule. And if it makes sense as well, if we look back, this 1H peak was likely this OH. Or this, wait, was it? What was it? I don't know what that was actually. Could have been the OH. Anyways, that will be our final product. Any questions on that? At all? Before we go to Diels-Alder? No questions? All right, we'll go to Diels-Alder. If you guys would like to leave, not learn Diels-Alder, that's fine with me. Really up to you. Just try to keep it quiet if you can for the ones that do want to learn about Diels-Alder. So the first one about Diels-Alder. So this is the facts question about Diels-Alder. So whenever we have Diels-Alder, we have a diene and a dienophile. So whenever we have a diene is likely gonna be a conjugated diene, which means that the double bonds are going to be one carbon away from each other, and there's going to be two double bonds. And the dienophile is going to have one double bond on it that wants to attach to this dienophile. So the main product of a Diels-Alder reaction is a cyclohexane, right? So the way it works is that if I was to redraw this real quick. Double bond right here. So this Diels-Alder was created, right? What happens is this double bond goes over here, tries to create that. This double bond attacks this, and then this creates this double bond right here. So it like essentially it does like a whole switcheroo, Three Stooges. You know what I mean? So then we have our cyclohexene created, right? And then we have two conjugated, right? So in this case, all we have to know is that a dienophile, which is that one carbon, which is that one double bond having thing, likes to have electron withdrawing groups. So these electron withdrawing groups are likely going to be like ketones or aldehydes or of that sort. You know, alcohols or esters, not alcohols, esters, carboxylic acids, right? It's going to want that. Versus a diene is going to want electron donating groups, right? And so these electron donating groups are going to be, they're going to be likely OCH3s, our ethers, our alcohols. These are going to be our electron donating groups, right? So our dienophile is what we're looking at, right? It's asking us to place the following compounds in order of increasing reactivity in a Diels-Alder reaction. So we're looking at a dienophile because it only has one double bond, right? So let's look at and identify which ones are dienophiles with the most electron withdrawing groups and which ones have the least. So the first thing we see is that this dienophile has two electron withdrawing groups, while the one on the left has one, and the one on the right only has one as well. So this is immediately going to be our best thing in the Diels-Alder reaction as a dienophile. So we'll put that as number 3. Then we keep going. On the left one, we have this CH2CH3. This is actually an electron donating group, but it's only an electron donating group by induction, right? So it's not very strong, right? Versus this OCH3, this ether, this is going to be an electron donating group by resonance. So this is going to be a stronger electron donating group. And for dienophiles, we do not like electron donating groups. So the weaker electron donating group is going to be better suited for a dienophile reaction, Diels-Alder reaction. So because it's by induction, this is going to be less reactive, and this is going to be our least reactive because it has it's an electron donating group by resonance. Any questions on that before I get to the final reaction question? No? Okay. So reactions. So one thing about Diels-Alder is that you're always going to want like the diene on the same side, right? So whenever we have a diene that looks like this, all we're going to do, we're going to flip it around, right? So this is going to go like this. We'll put the CH3 right there. We'll just trade places. And then our OCH3 is going to be like that, right? And then I just like to have it so that everything is exactly how it should be. So I'll put this like this, right? So that it's straight versus, and then the ketone on the other side, right? So we have our diene on the left, dienophile on the right, right? So whenever we do this, a Diels-Alder reaction creates the cyclohexene ring, right? So whenever this is created, the bonds that are made for the cyclohexene ring, they get onto dashes, right? And the ones that are, actually, I'll try to explain it. Let me show it like this, right? So we create this dicyclohexene ring kind of thing, right? So this double bond, it goes away because of the Diels-Alder reaction. So we have this double bond that forms a bond like this, right? This double bond forms a bond like this, and then this double bond creates our alkene, right? So we have one single double bond, and then we have the rest of the ring formed, right? And so one thing to note is that this ring that's on the right, everything on it is always going to be on a dash. And the way to show that, we have to put our hydrogens on wedges right here, right? So just make sure that you understand that the end is called the endo rule, right? So everything, whenever a Diels-Alder mechanism is done, it gets put onto a dash, and everything that was previously onto it is on a wedge, right? And now we have two separate things to add, right? So on the left side, we have our CH3. We can put that on the same thing. It's still going to be planar on that sp2 molecule, so we don't have to worry about the stereochemistry. Now we have this OCH3. So there's two steps to figure out if it's on a wedge or a dash, right? So whenever we have a diene, we have two positions that the substituents can be on. They can be vertical or they can be looking inwards, right? And that's true on both sides, right? So these can all be substituents. Let's just put H, 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 H. The only thing that you guys have to remember is that the ones pointing inwards, in equals wedge, right? And out equals dash, right? So I'll color code it. So the dash is going to be in blue. So this is going to go onto a dash, these two, and then this in on a wedge. These are going to go onto wedges, right? So whenever we have this OCH3 that's pointing down and out, it's going to go on a dash, right? So our OCH3 on this one is on this carbon right here. So we're going to put it on a dash, OCH3. And now we have one more rule we have to adhere to. It's that the electron donating group and electron withdrawing group have to be 1, 2, or 1, 4 away from each other, right? So what that means, the way to count this out is actually to skip this carbon. So my general tip is just to skip this carbon that your electron donating group is attached to, and just go immediately to the bond that's formed, okay? So we're going to immediately go here, all right? And this is going to be our number 1, right? So what we don't want to do is we don't want to count from internally, right? We don't want to count from 1, 2, 3, 4, like that, right? We want to count externally. So if we put this on the bottom here, we want to count from 1, and we start counting externally. 1, 2, 3, 4, 5, 6. Okay, so in this we can either have 1, 2 or 1, 4 on them, right? So they can either be on this 2 position right here, or they can be on this 4 position, right? So no other position. So whenever we look at our electron withdrawing group, this double bond O, this is in between the two alkenes, right? So this is between here and here, right? So because of that, it actually has to go on number 2. So our number 2 spot is going to be our ketone, right? So just like this, our ketone, and now we've created our 1, 2, cyclohexene ring, I guess, dual cyclohexene ring. And yeah, that would be the answer to this problem. Any questions on that at all? Any questions about the exam? No. Yeah. Yeah, you guys are not going to have this on the exam. It's going to be on the next one, though. Any other ones? All right. Well, good luck, everybody. Exam on Friday, Valentine's Day. Enjoy that. And yeah, that should be it.